step in this analysis, you are reducing or shrinking that unit volume down to an infinitesimal volume, right? When I say infinitesimal point, it is also down to the level that V is a point now. V is a point. The box here is not much more than a point in space. That is divergence. So the outflow from a point. So the divergence of vector A is the net flow of the flux of vector A out of a small volume, infinitesimal volume, through the closed surface enclosing the volume as the volume tends to zero. So that's the definition. In mathematical equation format, this is what it looks like. So the closed surface integral of the flux per unit volume as the volume tends to zero. Right? That's divergence. Now we also saw how there are two types of divergences. You could have positive, net positive, or net negative, right? A net positive is a source, right? A source, and a net negative, right, is a sink. Yeah, so you can have a non-zero positive divergence, non-zero negative divergence as well. So that's what we did in the last meeting. But this definition here, the boxed expression is
Is there any chance you could record this? I had somebody message me, said they were going to make it, and asked if you could. If not, it's fine.
This is something we should have. What can I say? Regimented from early on, right? It's fine to do recorded lectures, but I don't want to do this one-off things.
That's fine.
Let me see. So I've also done, depending on the situation, I've changed one or two of my lectures to virtual, right? I have done that, no problem. Exactly the same scenario that you are describing, the person had to be somewhere else, right, working on a project. So, okay, can I join virtually, he said. And I created a Zoom link for him, join from here, share the screen, no problem. So this goes back to my little rant on Friday, if you were here. A bunch of you guys took off for career fair, and I come here, there's like 10 people in the classroom. I won't complain about you guys going to the career fair, and you should. If you don't go now, when are you going to go to a career fair, right? But if you communicate that with me, we could discuss and come up with an alternative plan, right? A similar, so your colleague could have emailed me, can I join virtually? Of course, here's the link. But without that communication, I can't.
Of course, I'll let him know. Thank you.
Yeah. Very good. So this is our definition. That expression is not very useful, especially because divergence is something you can calculate at every single point in the field, right? You can't go around integrating all those points, right? So we need to come up with a different way of evaluating divergence, and that's what we will derive now. So first, let's write this expression in this format: divergence of A equals limit, closed surface integral A dot ds per unit volume as the volume tends to 0, right? I can write this as closed surface integral A dot ds. What is delta V? I can write delta V as delta x, delta y, delta z. That's the infinitesimal or the unit volume in a Cartesian system. So I'm going to say limit delta x tends to 0, delta y tends to 0, delta z tends to 0. Yeah? So now I would like to evaluate the divergence of the field A, right, that exists in the three axis Cartesian coordinate system, and I would like to evaluate the divergence of field A, vector field A at point P, right? So the volume that I have assumed, the volume that has those closed surfaces is this box here of volume delta B, okay? And the volume, you can zoom in, right? So that box you can zoom in, and the point P is P as a function of x comma y comma z, yeah? And now I have the box defined by x coordinates, so P itself is x, y, and z, right? That's that point in space. And now I need to draw a box around it. So the box has its limits, which are, x is, from point P, x, y, z, I draw a box with x limits. So I need to go from x to the right hand side, which is x plus delta x over 2, and then have to go to the left hand side, which is x minus delta x over 2, right? So these are the limits of this box in the x direction, and similarly you can say y plus delta y over 2, and then y minus delta y over 2, and then along the z axis you can go from z plus z delta z over 2, and then z minus delta z over 2. Okay, so those are the bounds of that box, and each of those surfaces, and right now we are very familiar at this point. Each of those surfaces is going to have a vector normal to that surface. So if you look at this box on the bottom right there, so your x-axis is, it's not very clear in this second image, so that's the x-axis, y-axis, and then you have the z-axis, right? So those are the coordinates from the image here. So there is a surface which is facing the positive direction of x-axis, yeah? So that is a different color. That is this face right there. Right, this face. Right there. So you have a surface which is perpendicular to the positive direction of x-axis, and that is represented by this vector. This vector delta y times delta z in the direction of x-axis, right? So this is that surface here. This is that surface. All points on this surface have the same x coordinate, yeah, same x coordinate, and you have delta y along the y-axis, and then delta z along the z-axis. So it's delta y times delta z, and the normal vector is along the x-axis. Okay. Similarly, you can have you can derive the other faces, right? So the face of this box opposite to this face is on the back. You have delta y delta z, and then the direction is minus x-axis. Similarly, you can have where is y-axis here? Y-axis is to the right, and you have a surface defined by delta x and delta z, and the direction is positive y-axis. On the left hand side of the box, I have a surface delta x delta z facing the negative direction of the y-axis. So you have these directions, right? These 6 faces. So the 6 faces or surfaces in that box are let's call them, let's give them names. I'm going to call them x plus, which is in the positive direction I have delta y delta z, x minus, that is in the minus x direction I have delta y delta z, yeah, and then y plus, that is in the positive y direction I have delta z delta x, y minus, that is in the negative y direction I have delta z delta x, and then finally z plus surface, that is in the positive direction of z axis I have delta x delta y, and then z minus, that is minus z direction I have delta x delta y. Yeah, so I have done nothing more than just writing the 6 surfaces. Yeah, see, let's walk through our definition of divergence. Divergence is, you take a point in space and the flow out of that point in space, right, of that field is divergence. Now you can calculate that by taking a volume. If you consider the original definition of divergence, we take a volume and then shrink it to unit volume and then shrink it down to an infinitesimal volume, right? So that's what this is. So I have these 6 surfaces and I need the flow through those 6 surfaces. That's the definition of divergence. Yeah. So how would that look like? I need to have the closed surface integral A dot ds. Yeah. So that is given by the sum of surface integral x plus, the surface integral x minus, surface integral y plus, surface integral y minus, surface integral z plus, surface integral z minus. Those are the 6 surfaces. Yeah. So now I need to evaluate them individually and come to the final addition. Yeah. So now let's take the first surface, which is x plus, right? X plus is our first surface defined by this shaded area there, this shaded area. Yeah. So now this integral x plus a dot ds x plus, right? This is what we need to evaluate. Yeah. Now, because we are using, instead of integration, we are using this small rectangular area, and within which the variable, the field is expected to be constant, we can write a x plus dot delta s x plus, right? The book has the same derivation, right? So you don't need to follow each and every letter here, but you can take this integral, right, and replace with this expression here, and you get basically the same result. Now we need the magnitude and the direction of this guy here. The direction of this vector delta s x plus is very clear, right? So that's x hat delta y delta z. This is what it is, right? This is that vector. Now we need this guy. What is the magnitude of ax plus? Right? What is this? So obviously this is a vector whose x component is of interest to us, right? So that's ax of, we have y and z, right? it's the same as this point, yeah, we are the same as this point. And then in the x direction, I have x plus delta x over 2. Okay, that is that vector coming out of the surface, or the component of A, right? The component of A, you see this field A, the component of A through that surface. Yeah, so that looks like that. Now we could approximate this. So I need A sub x as a function of x plus delta x over 2, y and z. But we know A sub x, x comma y comma z. That's because we have the point phi, right? We have the point phi. So the approximation here is A sub x, x plus delta x over 2, y and z equals A sub x, x y z plus delta x over 2 partial differentiation with respect to x of A sub x, x y z. You see what has happened here? I know the value of a function, let's say at point P1, and I need the value at, let's say, point P2. So what can I do? I can take the value at P1. I know the rate of change from P1 to P2. So I can just multiply the rate of change from P1 to P2 by the distance between P1 and P2 and add to the original value of P1, right? So typical, almost like an extrapolation problem, right? So if you're given a value of a function in one point, you can, and you know the function itself, you can calculate an extrapolated value, right? So that's kind of what is happening here. So you know the value at xyz, right? So the partial differentiation with respect to the x direction gives you the dependence of the function along the x direction, right? So that's the rate of change in the x direction. You multiply the rate of change by the distance, yeah? So that's what gives us this expression. So A sub x, function of x plus delta x over 2, y and z is equal to the value of the function of the original point, which is here in the middle of the box there, plus the step change going from the middle of the box to this surface, this shaded surface, that is delta x over 2. That's the distance between the two places. Yeah. So you end up with this value here, and now we can perform this. This integration. Yeah. How does that look like? Integration s x plus a x dot d s x plus equals. So we have x direction, and what is that expression in the back? A sub x, x comma y comma z plus delta x over 2 partial with respect to x of a sub x, x comma y comma z. Right? That's this whole thing that I have written is this vector here, a sub x. Yeah. Dot product. Yeah. Dot product. X hat delta y delta z. Okay, so we basically done this step here. This step written down in this manner. Yeah. So now we have two vectors, x hat direction and x hat direction. So you can just multiply the two magnitudes. Yeah. So we get delta y delta z a sub x x comma y comma z plus delta x delta y delta z over 2 partial with respect to x of a sub x x comma y comma z. Okay, so this is the flow of field A through the surface that was the shaded surface before, right? So this is the shaded surface which we are calling surface x plus. Yeah. Now similarly, you can do the derivation for the surface x minus. So the x minus, you will get a result that looks like this. So x minus integration is minus delta y delta z a sub x x comma y comma z partial over 2 partial with respect to x a sub x x comma y comma z. Okay, so that's what you did. Yeah, and now we can add the surface integral of surface x plus and the surface integral of surface x minus. Yeah, so I'm basically adding expression number 1 here and expression number 2 there, and you can see the first term vanishes. So you have a positive term here and a negative term here, so that vanishes, and then you end up with these two terms added together. So that would be delta x delta y delta z partial with respect to x of a sub x. Yeah, I'm going to not write the x, y, z anymore. Yeah? So that's one expression. Let's call it equation number A, right? And similar calculation or derivation can be performed for surface y plus and surface y minus. So you can add the surface integral y plus plus surface integral y minus. What you get is delta x delta y delta z partial with respect to y of a sub y. So that we're going to call it equation B. And you guys can guess where this is going. Z plus and z minus, you can add those two surface integrals. You get delta x delta y delta z partial with respect to z of a sub z. That we're going to call equation C. So you can add A with B and C. You will end up with, on the left hand side, you will end up with this whole expression there, right? So the surface integrals of surfaces x plus and minus, y plus and minus, and z plus and minus. Yeah, that we can replace with the closed surface integral of a dot ds. Yeah, on the left hand side. What do you get on the right hand side? You get delta x, delta y, delta z, r, p, z, or cylindrical axis, a cylindrical coordinate system is given as 1 over r partial with respect to r of r times a sub r plus 1 over r partial with respect to phi of a sub phi plus partial with respect to z. of a sub z. Okay, so that's the once again, it's not the same as the Cartesian coordinate system is not easy to write, but there is a certain simplicity to this, at least better than doing a closed surface integration. Spherical coordinate system. Spherical coordinate system, divergence is defined as divergence A in the r theta phi coordinate system is given as 1 over r squared partial with respect to r squared a sub r plus 1 over r sine theta partial with respect to theta of a theta sine theta plus 1 over r sine theta partial with respect to phi of a sub phi. Okay, I don't have to memorize it, but it's good to see how this came up. Yeah, we basically start with the Cartesian expression, which is this guy here. This I think you definitely should know how to do, commit to your memory, right? But from here you can, x, y, z can be mapped to r, phi and theta. Yeah, we know those relationships from the transformation matrix days. Yeah, and then you can apply that after some, I'm sure, complicated algebra. You end up with this expression. Okay, and there are some example problems we can do to understand this better. But for now, you need to really keep in mind what is the definition of divergence, and it is the outflow, let's say, of flux at a single point, right? So I have a point, how much flux is coming out of that point? Any questions? Okay, so the next idea I wanted to present is the divergence theorem. Divergence theorem. Okay, divergence theorem. So this relates to two ways of looking at the same problem. So if I have a field A, let's say, I have this vector field A that exists in a 3D or Cartesian 3D coordinate system. So I have x-axis, y-axis, and z-axis. All right. And I have a point P, just like before. I have a point P, and I draw this volume. I draw this volume here. Okay, I have this volume, volume V, right? Volume V. So A is a vector field in XYZ coordinate system, and V is a volume with 6 sides, right? 6 sides forming a closed surface, right? All right. So once you see this, you can say that a closed surface integral could be performed. right? Remember, that's the definition of flux, yeah? So the definition of flux is the closed surface integral, so flux or flow rate, right? Flow rate is the closed surface integral. So I can perform, so there's V volume, surfaces S1 through S6, right? So that box has 6 surfaces, S1, 2, 3, 4, 5, 6, yeah? So I can calculate the closed surface integral S A dot ds is surface integral S, let's say 1 to 6, yeah, A dot d S 1 to 6. Summation, yeah. This is the flux. So if I need the total flux through the 6 surfaces, I need to take the flux through each and every individual surface and add, right? So that gives me the total closed surface integral. So that's the flux. Now, there's another way to look at flux. What is divergence? Divergence is you take a point and the net outflow is divergence, yeah? So let's define that. Let's write this down here. So the book follows a different, slightly different algebraic way of doing this derivation, but we're going to just use our logic, right? What is divergence? Divergence of A is integral A dot ds, surface integral A dot ds over delta V as delta V tends to 0. So for an infinitesimal volume, right? That's the delta V tending to 0. So now we can have volume V defined in terms of XYZ. Volume V has limits defined by dx, dy, dz. So the box V has volume dV equals dx times dy times dz. Okay? So now, flow out of an infinitesimal volume is divergence, right? Flow out of an infinitesimal volume is divergence, yeah? Flow out of volume dV is equal to dV, which is divergence times dV, right? That's, if you follow the logic there, the flow out of an infinitesimal volume is divergence, and if you need the flow out of a volume dV, you're multiplying divergence by the volume dV. That's what we get. So what is total flux? Total flux is integral d phi, and that is integral divergence dV integrated over the volume V. That's the entire box. Yeah, that's flux. So you have equation number 2 and you have equation number 1. So they are both expressing flux. What we can do is write 1 and 2 together and say flux equals the volume integral of the divergence, yeah, is equal to the closed surface integral of A dot ds. Okay, this is the divergence theorem. Okay. To put it in other words, if you would like the closed surface integral of the field over a surface S, it is enough to calculate the divergence of the field throughout the volume. Yeah. And in a way, it, logically, if you think about it in terms of, let's say a container filled with positive charges, right? So if you have a positive charge, you're going to have field lines coming out of the positive charge. And you have a container full of positive charges. If you would like the total flux lines, what can you do? You can take each and every positive charge and then add up the flux lines due to each and every positive charge. That's this guy here, right? Divergence is each point has an outflow, yeah? Or you can take that box of positive charges and you can just measure how much flux is coming out of the surfaces. Yeah, it's going to result in the same value. Yeah, so that's the divergence theorem. So why do we need both? Because depending on the problem or the situation, it might be easier to do the derivative, right, which is divergence, or the integration, which is the closed surface integration. Okay, so we'll once again do some problems to verify the divergence. All right, I'll see you guys Wednesday.